morning students. Myself Satnam Singh, lecturer electrical engineering from Government Polytechnic College Mohali, Punni Today we will discuss the topic miscellaneous measuring instrument. In this lecture we will discuss the miscellaneous measuring instrument, measurement of resistance with the help of Megger and earth testers, frequency meter, power factor meter, phase sequence indicator, and instrument transformer. In instrument transformer we will discuss the current transformer and potential transformer. So first is measurement of resistance. So resistance is defined as the property of conductor or material by virtue of which it opposes the flow of current. And resistance is the formula of resistance is rho L upon A, where L is the length of conductor, A is the cross sectional area. So resistance is directly proportional to length and inversely proportional to area. From the point of measurement, resistance can be classified as low resistance, medium resistance, and high resistance. So for the measurement of resistance, we classify the resistance into three categories. First is low resistance. In low resistance, resistance having their value of about 1 ohm or even less than that are known as low resistance. The armature winding, series field winding, or large machines and shunt of ammeter comes under these categories. Second is medium resistance. Under the medium resistance, the resistance value from 1 ohm to 100 kilo ohms are included in this class. Most of the electrical apparatus used are of medium resistance. Third one is high resistance. The resistance value above 100 kilo ohm comes under the category of high resistance. Under these categories comes insulation resistance, volume resistivity of material, and surface resistivity. So first is measurement of low and medium resistance. The various methods used for the measurement of low resistance are by ammeter voltmeter method, second is by Wheatstone bridge method, and third one is by double Kelvin bridge method. So measurement of low resistance by ammeter voltmeter method. In this method, as you can see from the figure, that it consists of ammeter and voltmeter. The resistance whose the apparatus or instrument whose resistance is to be calculated, ammeter and voltmeter connected, ammeter connected in series with the resistor, and voltmeter is connected in parallel with the resistors. So we when we connect the battery across this circuit, ammeter will measure the current and voltmeter will measure the voltage. So as we know, resistance is equals to voltage upon current. So if we divide voltage, which is measured with the help of voltmeter, by current measured with the help of ammeter, then the value of resistance will be found out. In this method, current through resistor under test and the potential difference across the resistance are measured with the help of ammeter and voltmeter. The ratio of potential difference to the current gives the value of resistance. So resistance is equals to voltage upon current. Next is measurement of low resistance with the help of Wheatstone bridge. So this is a diagram of Wheatstone, which you can see that it consists of four resistors, P, Q, R, and X. Here P and Q are fixed resistor, R is the variable resistor, and X is the unknown resistance whose value is to be measured. Here point A is the point at higher potential, point C is at lower potential, and the potential at point B and D are kept same by varying the value of resistance R and keeping the value of resistor P and Q same. So if we keep the value of P and Q same and we vary the value of resistor to such extent that the galvanometer shows zero deflection, then the point B and D will be at the same potentials. Wheatstone bridge consists of four resistance P, Q, R, and X connected in series and parallel. Resistance P and Q's are fixed, whereas resistance R is variable. X is the unknown resistance whose value is to be determined. There are two branches, namely ABC and ADC. So In both the branches, point A is at the highest potential and point C at the lowest potential. There is therefore continuous fall of potential along each branch. By adjusting the value of P and Q to suitable value and changing the variable resistance R, such a condition can be obtained that point B and D are at the same potential. Under such a condition, a conductor joining B and D will carry no current. In order to determine whether point B and D are at the same potential or not, a galvanometer is connected between point B and D through a key K2. It is called bridge because galvanometer is sort of bridge between B and D. So galvanometer is sort of bridge built up between B and D, and key to will connected in series with the galvanometer. When we close the key K2 at the point when point B and D are at the same potential, the galvanometer will shows the zero deflection. This point at where the galvanometer shows zero deflection is known as null point. So at this point, the ratio of opposite branches, that opposite resistance, that is P upon X and Q upon R, will be equals. The Wheatstone bridge is said to be balanced if the galvanometer shows no deflection on closing the key K2. It should be noted that the bridge can be balanced by properly fixing the value of P and Q and changing the variable resistance R. The balanced condition of the bridge is sometimes called null point. The current in the various branch are indicated according to the first law, Faraday first law, Kirchhoff first law, that is current entering at the any point is equals to current leaving at that particular point. So consider the closed loop A B D A. According to Kirchhoff voltage law, the sum of all the potential drops across this closed loop will be equals to 0. So potential drop across resistor P, that is I1P plus IgG and plus I minus I1 into R will be equals to 0. Similarly, for closed circuit BCDB, we have minus I1 minus of I1 minus Ig into Q plus I1 minus I1 plus Ig into X plus Ig into G will be equals to 0. So potential drop across all the resistor in a closed loop will be equals to 0. In balanced Wheatstone bridge, the current through the galvanometer will be equals. So at the point where the potential at point B and D equal, then there will be no current in the galvanometer. At this point, Ig will be equals to 0, and by putting the value of Ig equals to 0, the equation 1 becomes equals to I1 into P plus R equals to R, and equation 2 will becomes I1Q plus X equals to Ix. Dividing the equation 3 and by 4, we have P plus R by Q plus X equals to R by X. So if we divide the equation 3 and 4, then I1 and I1 will cancel out, I and I will cancel out, and the equation will become P plus R upon Q plus X equals to R by X. So if we cross multiply this, then this equation will becomes Px plus Rx equals to Rq plus Rx. So Rx will be cancelled out, and the equation will become Px equals to Rq. So this will becomes P upon Q equals to R upon X. As we know, the value of P, Q and R is known, the value of resistor X is unknown. So we can derive the formula from this, that is X is equal to R into Q upon P. So the value of unknown resistance can be determined by the balancing the Wheatstone bridge. Next is measurement of very low resistance by using the method Kelvin double bridge methods. In Wheatstone bridge, error like contact resistance, resistance of connecting leads, etc. occur. It do not allow the use of Wheatstone bridge for the measurement of very low resistance. The measurement of very low resistance can be had by using the double Kelvin bridge. Figure shows the double Kelvin bridge. Uh, Here X is the unknown resistance and R is the standard resistance of the same order of resistance and should be of same rating or of the higher current rating. The two resistance X and R connected in series with the short link resistance having resistance small r of very low resistance value. Resistor P, capital P and capital Q, small p and small q are the four non-resistance. Out of these two, one pair, that is pair of capital P and small p, or pair of capital Q and small q resistor is variable. So one of the pair, either capital P and P should be variable, or capital Q upon capital Q and Q resistor will be variables. The rating current is made to pass through the two resistance X and R respectively from the battery. A variable resistance and ammeter connected in the circuit limits the flow of current. A galvanometer is also connected between the point PQ and small pq, or between the you can say between the terminal FK. So galvanometer is connected between the point between the PQ and capital PQ and small pq, or you can say between the point F and K. The ratio of P by Q is kept same as that of small p and q resistors. These ratios are varied continuously till the galvanometer shows the zero reading on the scale. When galvanometer indicates zero position on scale, it is called null point and meter is said to be balanced. In balanced position, that is when galvanometer shows zero deflection, the direction of flow of current in the bridge are shown in figure. Applying Kirchhoff's second law to the mesh A, H, F, K, B, A and F, F, E, D, C, K and F, the current is the equation is I2P minus I1 small p minus Ix is equal to 0, and Ix is equal to I2P minus I1 small p, and in the second mesh FEDCKF, the equation is I2Q minus I1Q minus IR equals to 0, or we can write IR is equal to I2 Q minus I1 small q. So if we divide the equation 1 by 2, then we will get the ratio of x by r. So I2P minus I1P divided by I2Q minus I1Q. If we take the P common from this from the numerator, then I2 minus I1 capital P small p minus divided by P, and the denominator, if taking the common capital Q resistor, Q I2 minus I1 small q by Q. As we know, ratio of P by Q and P and small p by Q is same, therefore x by R equals to P by Q. So from this equation we can find out the value of x, which is unknown resistance. Next is ohmmeter. This is the portable instrument which indicates the value of resistance to be measured by means of pointer and scale. This instrument indicates medium and high resistance. The ohmmeter is essentially a permanent magnet moving coil instrument but without the control spring. Figure shows an ohmmeter. It consists of two coils, the current coil C and pressure coil P, fixed at right angle to each other. There is pivoted magnetic needle to which a pointer is attached, moving over a scale extending from 0 to infinite. The supply is given to the terminal A by means of small permanent magnet hand driven generator generating about 500 volt. The action of ohmmeter is as given below. The ohm resistance is connected between the terminal XX, supposing the unknown resistance to be infinite, that is circuit is open, then generator voltage will be across the pressure coil only, and no current will pass through the coil C. The field generated by this coil exerts torque on the pointer so that it aligns itself along the axis of the coil P, and the pointer points to infinite. In other case, if terminal XX are shorted, this will result that all the current will flow through the current coil C. The field will exert torque on the pointer so that it aligns itself along the axis of coil C, and the pointer points to the 0 on the scale. The scale is graduated in ohms. The intermediate point may be obtained by calibrations. So ohmmeter consists of two coils, current coil C and pressure coil P. Thus, the supply is connected at terminal A plus A and minus A, and supply is taken from the hand driven generator, and unknown resistance is connected across the terminal X and X. So if the point XX are open circuit, or if or infinite resistance is connected in a circuit, then the whole current will pass through the pressure coil P, and current through current coil will be 0. So the magnetic needle tries to align in the along the axis of pressure coils, and it will deflect in the infinite reading side. So the reading on the ohmmeter will be infinite. That is the resistance of the resistance, which is the value of resistance, the value of resistor whose resistance is to measured is infinite. So if we connect, if we short the terminal X and X, then the whole current will pass through the current coil, and the current through pressure coil will be 0. In this case, the magnetic needles will tries to align in the direction of current coil, and it will indicate the value of 0. Next is Megger. Megger is an instrument used for the measurement of high resistance and insulation resistance. It consists of hand-driven generator and a direct reading 2-ohm meter. Figure shows the electrical connection of Megger. The magnetic field for both, that is generator as well as meter, is provided by the permanent magnet. The moving system of Megger consists of three coils, that is current coil, pressure coil, and compensating coil. Current coil will produce the deflecting torques. Pressure coil will produce the opposite torque, which oppose the deflecting torque, and compensating coil will provide the proper calibrations of the meters. The coils are connected to the circuit by means of flexible wire that exert no restoring torque on the moving system. Hence, the moving system may take up any position over the scale when the generator handle is stationary. The current coil is connected in series with the resistance R between generator terminals and test terminal marked L and E. When the terminal are short circuited and the generator handle is moved, a heavy current passes through the current coil. The resistance R also controls the range of the instrument. The pressure coil is in series with the compensating coils, and protection resistance R and is connected across the generator terminals. Compensating coil is provided to obtain the better scale proportions. When the current from the generator flows through the pressure coils, the coil extends to set itself at right angle to the field of the permanent magnet. When the test terminals L and E are open corresponding to infinite resistance, no current will flow through the deflecting coils. The torque so produced rotates the moving system of the magnet until the scale point infinite, thus indicating that resistance of the external circuit is very large for the instrument to measure. Now, when the testing terminal L and E are short-circuited through a low resistance, then a heavy current passes through the deflecting coils or current coil to produce sufficient torque to overcome the anti-clockwise torque of pressure coils. The moving system points to zero, thus showing that external resistance is too small for the measurement to measure. When a resistance under test is connected between the terminal L and E, the opposing torque of the coil balance each other, that is, torque produced by the current coil and torque produced by the pressure coil will balance each other, so that pointer comes to rest at some intermediate point on the scale, and thus the pointer indicates the value of resistance under test. Now, operation of measure. The resistance under test is connected between the test terminal L and E. The generator handle is moved, is steadily turned at a uniform speed. The turning of handle is then steadily turned at a uniform speed. The turning of handle must be kept up until the pointer gives steady reading. The reading on scale gives resistance in mega ohm. Now next is earth tester. The earth tester is special types of ohmmeter which sends AC through earth and DC through measuring instrument. It has four terminals, namely P1, C1, P2 and C2 brought outside. Two terminal P1 and C1 are shorted to form a common point which is further connected to their earth electrode as shown in figure. The other two terminals P2 and C2 are connected to terminal P and C respectively. The handle is made to rotate at a uniform speed. The direct indication of earth tester gives the earth resistance. You can see that the terminal P1 and C1 are short circuited and connected to the terminal E. The terminal P2 is connected to the point P and C2 to the point C. Uh, so earth tester is used to measure the resistance of the earth. Although tester, which is permanent magnet moving coil instrument and can operate on DC only, yet by including the reverser and rectifying device, it is possible to make measurement with AC flowing in the soil. The use of AC passing through the soil eliminate unwanted effect of due to the production of back EMF in the soil on account of electrolytic actions. Now, next is measurement of frequency. The frequency of an AC circuit can be measured by various methods, as the frequency of supply from a local alternator can be determined by knowing the number of poles of the alternator as well as the speed of the given alternator. The frequency F is equals to NP by 120, where N is the number of n is the number of turns, n is the speed, and p is the number of poles. The other method of measuring frequency of the order of 50 to 100 cycle per second is with the help of portable instrument known as frequency meters. The frequency meter operate on the following principles. First one is mechanical resonance, second is electrical resonance. A frequency meter based on mechanical resonance type. This type of instrument operates on the principle of mechanical resonance. It consists of number of thin steel strips placed in a row alongside and close to electromagnet as shown in figure. These steel strips are known as reed. The bottom portion of reed is fixed whereas the upper portion of the reed is kept free to vibrate. So it consists of electromagnet and the steel strip. These steel strips are known as reed, and this upper portion is known as flag. A band is given to upper portion of the reed and are painted white at the top to distinguish them against black background. The electromagnet of vibrating reed frequency meter is wound with a large number of fine wires and is connected in series with the resistance across the supply whose frequency is to be measured. The dimension of all the reeds are not similar but differ slightly so that mechanical vibration of each reed is different. The reeds are so designed and arranged in an ascending order of natural frequency. So the size of each reed is different and is according to the mechanical vibration of and is different according to the natural mechanical vibrations. When the frequency meter is connected across the supply whose frequency is to be measured, an alternating flux is set up. Due to this alternating flux, an attractive force is experienced upon the reed every half cycle. The result is that all the reeds tends to vibrate, but only the reed whose frequency is double of the supply frequency will vibrate with the maximum amplitude. If the two adjacent reeds vibrate with the equal magnitude, then the supply frequency will be halfway between the frequency of two adjacent reeds. Figure shows when the supply frequency is 50 Hz, then the vibrating reed having natural frequency 50 Hz vibrate with the maximum amplitude. So figure A shows that the supply frequency is 50 Hz and the reeds having the natural frequency of 50 Hz will vibrate and all the other reeds will not vibrate. Now figure B shows that when the frequency is 49.50, then the reed having frequency of 49 and 50 vibrate with equal and maximum amplitude. So if the frequency is in between the 49 and 50, then both the reed having the frequency 49 and 50 will vibrate, and the measurement of the frequency is come out to be 49.50. Figure C shows that no reed is vibrating, which simply means that either exciting coils are not energized or frequency under measurement is out of range of the measurement. So figure C is no reed is vibrating, which means that either exciting coils are not energized or frequency under measurement is out of range. Now frequency meter electrical resonance type. This type of instrument operate on the principle of electrical resonance. When inductive reactance XL and capacitive reactance XC becomes equal, the electrical resonance said to be occurred. So when the inductive reactance XL becomes equals to capacitive reactance XC, then the electrical resonance is said to be occurred. This type of instrument consists of laminated iron core of varying cross section, a fixed coil known as
magnetizing coil mounted at one end of the iron core, moving coil attached with a pointer and pivoted so that it can move freely over an iron core. The moving coil is further connected to a suitable capacitor C, whereas magnetizing coil is connected across the supply terminal